Mr. Dion, I don't understand, or could you re-explain? And I'd be happy to do that. So, Chemistry 3111, we're getting closer to the end of Organic Chemistry 2 now, and we're going to start talking about amines, right? And you know what amine, right? When we're talking about amines, because you learned about the amine functional group way back in Organic Chemistry 1, when we first started talking about functional groups in the first chapter. You know that this is a primary amine when we have one R group on our nitrogen, but if we have two R groups and only one hydrogen, this is a secondary amine. And then if you have three R groups attached to your nitrogen, that is a tertiary amine. And remember that the nitrogen always has 3 bonds in 1 lone pair. So to be correct, I should put the lone pair on each one of those. And so that's what it says on my first slide, right? Primary, secondary, and tertiary amines are nothing more than derivatives of ammonia. Now, ammonia is a gas at room temperature, right? If you just have pure ammonia, it is a gas, NH3 gas. However, you can bubble ammonia through water to get ammonium hydroxide. And so you can have an aqueous solution of ammonia. Anyhow, so you need to know the difference between ammonia and then primary, secondary, and tertiary amines. Something else that's interesting about ammonia, primary, and secondary amines is that you notice they all have at least one. They all have nitrogen-hydrogen bonds, don't they, right? Primary amine has 2, ammonia has 3, and a secondary amine has only 1, but they all have nitrogen-hydrogen bonds. So ammonia, primary, and secondary amines are all capable of hydrogen bonding, right? You could put that here, and you could say these ones can all do H bonding with each other, whereas a tertiary amine does not have a nitrogen-hydrogen bond, and therefore it does not participate in hydrogen bonding. And that actually loans tertiary amines some interesting physical properties that we'll talk about later on. Now, if you're interested in naturally occurring amines, they call those alkaloids, and there's some interesting history behind naming them alkaloids, and you can take a look at that in the textbook. But these are 3 very well-known molecules. You know, if you look at morphine, which is shown here, you can see that morphine is cool in that not only does it have a nitrogen in the molecule, that it's also got a bicyclic structure, right? You see how there's a ring with the nitrogen that's coming off of the other 4-membered, or the 4-ring, you know, system there. Another thing is if you replace both of these hydrogens with acetyl groups, so if you literally just put, you know, if you put an acetyl group here, in another acetyl group here, that's heroin. So heroin is pretty close to the structure of morphine, and I've probably told you that before at some point. If you look at cocaine, cocaine is another bicyclic compound. You see you've got the 5-membered ring here, and then you also have the 6-membered chair right here, and then all it's got is a couple of esters. You've got a methyl ester here, and you've got a benzyl ester here, a phenyl ester. And what else? You have a methyl group on the nitrogen. So it's not the most complicated compound in the world. Okay, and then you have nicotine, which is a really addictive compound that's found in tobacco. And this is one of the reasons why people have a hard time letting go of cigarettes, is because of the nicotine that is found in them. Anyhow, we look at nicotine, and it's got a 5-membered ring with a nitrogen in it, and it's got a pyridine here. It doesn't look like a very complicated compound, but a very highly addictive compound. Anyhow, some naturally occurring amines are vital to neurochemistry, like the ones that are shown here. We have adrenaline and noradrenaline and dopamine, and you can probably guess what this one is that I have down here. This is methadone or methamphetamine that I have shown here. So, which, anyhow, that's enough. But anyhow, that's methamphetamine. Anyhow, the drug is racemic. You know, when people take it, it's racemic. Anyhow, I could go in more about the history of that, but we'll just move on today. Anyhow, so if you thought about the molecular geometry of the nitrogen in an amine, right? If I was to ask you to draw the Lewis structure of, you know, an amine, you draw something like this. If you had a tertiary amine where you have an R group here, an R group coming out in front, then you have the lone pair up here. So the electron geometry is tetrahedral, but the molecular geometry is trigonal pyramidal. Now that nitrogen is attached to 4 different groups, isn't it? It's attached to a lone pair, it's attached to an R group, another R group, and another R group that could all be different. But anyhow, we'll talk about that more later on. But we know that the nitrogen has sort of a partial negative charge, right? Because nitrogen is an electronegative element to some degree, and it pulls electron density in towards itself, and therefore the lone pair on the nitrogen of an amine can function as a base or a nucleophile. Now, this is something that you would have seen almost Avogadro's number of times way back in General Chemistry 2. You talked about amines and how they can react with a strong acid to make, this is some kind of ammonium chloride salt, okay? But we've also seen cases where nitrogen can behave as a nucleophile. So here it is just doing an SN2. If you take methyl chloride, that's a very powerful electrophile. We have the nucleophilic attack occurring here, and then we have the loss of leaving group occurring here. So again, an amine can function as a base or as a nucleophile depending on the situation. If you look at an electrostatic potential map of trimethylamine, it's this little guy here, you see how much electron density is in the center of the molecule. It's all on that nitrogen in the middle because nitrogen is so electronegative. Well, the nomenclature of amines, like I told you, can get pretty tricky. Naming primary amines isn't all that bad. It's naming secondary and tertiary amines that can get a little bit trickier, and I'll show you how to name those. So there's two different ways to name a primary amine. The first one is to name it as an alkylamine. So you literally give the name of the alkyl group first. Okay, so this is, using the alkylamine way, like this. So you name, this is an ethyl, this is an isopropyl, this is a cyclohexyl. So we've got ethylamine, isopropylamine, and cyclohexylamine. But what if the R group, attached to your amine, what if it's something that's not that simple? Well, in that case, you want to name it as, instead of you want to name it like this. So you name it as an alkanamine. So more complicated amines are named as alkanamines. They are named the same as alcohols, but the suffix amine is used instead of all. So if we look at the longest carbon chain here that contains the amino group, it's got 7 carbons. So this is some kind of 2-heptane amine, right? Instead of 2-heptanol, you would 2-heptane amine. And then we have 2 methyl groups. This one is not a stereocenter, but the stereochemistry at both carbon number 2 and carbon number 4 is R. And so we have 2R, 4R, 4,6-dimethyl, 2-heptane amine. So again, it's just like an alcohol, except you replace amine with, you replace all with amine. And again, that longest carbon chain has to contain that nitrogen group on it. Well, if you have an amine in a compound that has any functional group that's got oxygen in it, okay, the amine is always the loser. Okay, what does that mean? Put a nicer way, maybe. The oxygen-containing group will always be the parent. So if you have a carboxylic acid or an aldehyde or a ketone or an alcohol or an ester, okay, or an amide or something like that, anything that's got oxygen in the functional group, it will always take precedence over an amine. Okay, so if you have an amine and an alcohol in the same compound, it's going to be an alcohol. If you have an amine and an acid in the same compound, it's an acid. Okay, that's why if you think about, if any of you have studied biology and you've talked about amino acids, that's why it's called an amino acid and not an acid amine, because the acid is the parent. Okay, that's just a quick and dirty rule. And this is the order of precedence down here. But again, anything with oxygen is always going to take precedence over an amine-containing group. If the amine is directly attached to an aromatic ring, of course, you know that that is an aniline of some sort. So here we have aniline, metachloroaniline, 5-ethyl-2-fluoroaniline, right? And of course, you want to number it in such a way to give the first substituent the lowest possible number. The nitrogen on the ring, or the carbon with the nitrogen on it on the ring is always carbon number 1. So we have 1, 2, 3, 4, 5, like that. Here you'd have 1, 2, 3. So you could also call this 3-chloroaniline. Okay, either way is perfectly reasonable. Now, when you're naming secondary or tertiary amines, there's a couple of different ways to do it, and it depends on whether they're simple or complex, really. One way is to name the alkyl groups, okay, in alphabetical order. And then if there's more than one that's the same, you say di or tri. So for example, if you have 3 methyl groups on your amine, it's trimethylamine. If you have 2 ethyl groups, it's diethylamine. Here you've got a propyl, you've got an ethyl, and you've got a methyl. You list them in alphabetical order. First you put the ethyl, then you put the methyl, then you put the propyl. So ethyl, methyl, propylamine. There you go. All right. Yeah, so that's kind of finishes that. Now, what you want to do if you have something that's more complicated, you want to find the carbon parent chain, use the suffix amine, just like we saw a few slides ago. And then the smaller groups that are attached to the amine can be named with an N locant. So here we have a methyl group on the nitrogen, so we call it an N-methyl. The N is usually italicized. And then here we have an ethyl. So to denote that it's on the nitrogen, we call it an N-ethyl. And then the rest, we just give it the same old name, right? We imagine that this is a primary amine, so we have 6 carbons. So instead of like a hexanol, this is a hexanamine. It's a 3-hexane amine. We have a 2,2-dichloro. We denote the stereochemistry, which is S. And then we have N-ethyl and methyl. So we list the substituents in alphabetical order. So the chloro comes first, ethyl comes second, and methyl comes last. N is like a prefix, okay? You don't alphabetize according to the N, all right? You just treat that as if it's a prefix. So with that in mind, let's take a look at the nomenclature of a few amines. The first one and the second one are tertiary amines. Let's go with number 2. For D, we'll start with D first. Could anybody give me an idea of what kind of name you might want to use for D? Based off of the rules that we just saw. Yeah, so Skylar, could you give me a common name first? Skylar, you're totally in the right vein. So what I would do first is I would go back here and I'd say the simplest way is just to name all the alkyl groups. Like you got 2 ethyls, so it's diethylamine. Yeah, exactly. So this is the way I would do it. I'd say I have 1, 2, 3 ethyl groups. So I would call it triethylamine. Right, and that's the simplest way to do it. But there is another way, and you're 100% correct. You could take the longest carbon chain like this and say this is an ethanamine, right? Instead of, right, if you have this compound is ethanol, right, that would make this ethanamine. So in that case, we'd call it N-ethyl, N-ethyl. So it's NN-diethyl. So we have NN-diethyl ethanamine, like that. I can't imagine anybody calling it that. But if you look it up on the internet, like on Wikipedia, for example, you will see this name in there as being an acceptable name. However, most chemists will refer to it as triethylamine, and they'll even shorten it to an acronym, which is TEA. So if you ever see TEA, it's not tea like you drink, it's TEA, which is triethylamine. Let's go up to C. Let's try the next one. Let's do C. This one, I mean, you could name this as, if you have this compound, for example, this would be cyclopentanamine. Okay, cyclopentanamine, you get the longest carbon chain here. So we could call this NN-dimethyl cyclopentanamine. So NN-dimethyl cyclopentanamine. Or we could give it a common name because we've got a cyclopentyl group and 2 methyl groups. So cyclo is a prefix that we don't ignore. So we have cyclopentyl. So let me write that down. Cyclopentyl, pentyl, dimethyl amine. And that would be perfectly reasonable as well. And then the last one is trickier because we have two chiral centers. So we have one amino, three isopropyl. So we have a cyclohexane is our longest chain, which is this one here. So think about it. If you had this, this would be cyclohexanol. So this must be cyclohexanamine. Okay, so this is some kind of cyclohexanamine. And we would give the nitrogen carbon, we give that the number 1, 2, 3. So this is a 3 isopropyl cyclohexanamine. So we'll put that down. 3 isopropyl cyclohexanamine. Okay. The only thing that missing is we need to figure out the chirality of the two stereocenters. So we've got 1 something, 3 something. So if we look at the first one, the amino group is highest priority. This is second highest. This is third highest. So we're going like this, which is S. So it must be 1S. So let's write that down. And then the next one, you go from carbon, carbon, hydrogen, carbon, hydrogen, hydrogen. So you go from 1 to 2 to 3. So that's like this, which is R. And so the next one is R. So there you go. We have 1S, 3R, 3 isopropyl cyclohexanamine. You want me to tell you a trick that I always use when I'm naming amines? Okay. Whenever I get, and I mean, I don't do this as much, but when I was a student, if I was ever confused on amine nomenclature, I would always just think of an alcohol. How would I name this if it was an alcohol? Right? If I had this compound and it was alcohol, it would be a cyclohexanol derivative, right? And that's kind of, I think the easiest way to do it, right? If you had this compound and it was an alcohol, if you had this compound, son of a gun, I keep writing with a highlighter. If you had this, you'd call that cyclopentanol, right? If you have this, you call it ethanol. So you get cyclopentanamine, ethanamine, right? That's, I think, the easiest way to do it if you're ever stuck on amine nomenclature is just think of it like an alcohol. Next one, it says draw the structure for each of the following compounds. First, we have tricyclobutylamine. So a cyclobutyl is this, where we have a 4-membered ring. So this is a cyclobutyl, and we have 3 of those on our nitrogen. So we have 1, 2, 3. On the first one, we have a cyclobutyl. On this one, we have a cyclobutyl. And on this one, we have a cyclobutyl. So tricyclobutylamine. The next one is 2,4-diethylaniline. So if we draw aniline, it looks like this. Okay, so there we go. There's our NH2. So if the carbon with the amino group on it is number 1, 2, 3, 4, 5, 6, we've got an ethyl group at carbon 2, and we've got an ethyl group at carbon 4. There we go. So we get 2,4-diethylaniline. And the last one is a cyclohexanamine. So that means it's going to look like this. We've got a amino group here, like a cyclohexanol. So we've got 1R, 2S, 2-methyl cyclohexanamine. So what I like to do is this. I will start like this. I'll put in the amino group, and then I'll put in the methyl group like this. I'll put them both on wedges so that if they're wrong, I can just shade them in. So let's see here. If I take the first one, if it's 1R, I go from 1 to 2 to 3. So it would go like this. So my proton is coming out in front, so I reverse it. So that means I have to shade that in. So let's shade that in. So now this is a 1R. And then with the methyl group, I go from 1 to 2 to 3. So it means I'm going from here to here to here, which is that right? So what am I doing wrong here? Let me think. I've got my proton coming out here. So I got 1, 2. So that's, yeah, that's R the way it's written. Okay, right? Because look, I'm going from here, which is highest priority, here, which is second priority. This is third highest priority. So I'm going like this, which is S, but then the proton's coming out in front. So it's actually R the way I have it written, which is R for wrong, right? So it's incorrect. So now I have to fix it. And so what will I do? I'll just shade in the methyl group. There we go. All right, give me a thumbs up if you follow me on that, on the amine nomenclature. Is everybody with me on that? Amine nomenclature, great, thanks, Skylar. All right, you know, amine nomenclature takes a little bit of time. It's not as complicated maybe as the nomenclature of carboxylic acid and acids and their derivatives, which takes forever to get through. But you do need to practice the nomenclature of secondary and tertiary amines for sure. Well, the next section, just like when we looked at the alcohols and we talked about their nomenclature, the next thing we always talk about is the properties, right? And I told you that the molecular geometry is trigonal pyramidal. The nitrogen is sp3 hybridized, and you guys should know that the lone pair is in an sp3 hybridized orbital. Now, the bonds around the nitrogen, bond angles like this one here and this one here, they're around 108 degrees. Why? Because we have the repulsion of that lone pair pushing those methyl groups closer together than 109.5 degrees. Now notice that the carbon-nitrogen bond lengths are slightly shorter than carbon-carbon bond lengths, which are around 153 parts per million, and carbon-oxygen bond lengths, which are around 143 parts per million. So they're kind of somewhere in between, okay? Now it says here, under what circumstances would the nitrogen be sp2 hybridized? Now, this is a question that I've asked my students in the past, but in case you've forgotten, remember that when you have an amide, okay, the nitrogen on an amide, I'll just draw a secondary amide here, it might be a knee-jerk reaction to look at this and say, well, the steric number is 4. I've got a lone pair and 1, 2, 3 bonds. Therefore, it must be sp3 hybridized. But hold on. You know that an amide, the nitrogen has very little of the electron density because it can participate in resonance like this with the oxygen in order to make this resonance contributor. And I know you could all draw it faster than me. But you see that a lot of the electron density is up on the oxygen, okay? And so the bottom line is that the nitrogen in an amide is actually sp2 hybridized, okay? Because here in this structure, you have a double bond and 2 single bonds, and the steric number is 3 here. All right, so that's a specific case that we went over. If you don't believe me, go look back in chapter 1 of Organic Chemistry 1. It was towards the end of the first chapter, I think, that we spoke about that in Organic Chemistry 1. So some properties of amines. All right, this is something I was talking to you about earlier today. I said, well, if you think about the nitrogen of an amine, okay, and if I just draw out the lone pair like this, if I draw R1 and then in the back here, I put R2, and then out here, I put R3. Well, if all 3 of those R groups are different, then that nitrogen is actually chiral, isn't it? Because it's attached to 4 different groups. The lone pair does count as a group. But amines are generally not optically active, right? They're generally not optically active. We don't think about going around and assigning nitrogens R or S stereochemistry. And the reason why is because the inversion between the 2 trigonal pyramidal forms just happens so quickly. The barrier for inversion here is only 25 kilojoules per mole, which actually isn't even all that much. And so you're going to have a 50-50 mixture of these 2 trigonal pyramids that are rapidly interconverting, I should say. And so essentially it takes away the chirality of the molecule. Now, what about the solubility of an amine, right? Amines are capable of hydrogen bonding. It says here that amines that have less than 5 carbons are generally speaking going to be soluble in water. Primary and secondary amines, like I mentioned earlier today, they can participate in hydrogen bonding. but they have higher boiling points than tertiary amines. Why? Because tertiary amines cannot participate in hydrogen bonding. That's shown down here on the bottom. If you look at propylamine or propanamine, it is a primary amine. Ethylmethylamine is a secondary amine, and trimethylamine is a tertiary amine. These are all isomers of each other. They all have the same molar mass, but if you look at the boiling point, the highest boiling point is the primary amine. Why? Because it has 2 opportunities for hydrogen bonding, whereas the secondary amine only has 1 opportunity, so the boiling point is decreased. But if you look, it drops way off, down to 3 degrees Celsius for the trimethylamine, because there's no opportunity for hydrogen bonding. So no hydrogen bonding in a pure sample. Now, if you're wondering what the first 3 compounds are for, all it's showing is a comparison of an alkane, which is propane, with propanamine. Okay, so an amine, which is what we're looking at in this chapter, and then an alcohol. And if you look at the 3 of these, the alkane has the lowest boiling point. Why? Because it has no polar bonds in the molecule. It only has London forces, nothing else. Whereas the amine has London forces, dipole forces, and it also has the opportunity for hydrogen bonding. Whereas the alcohol also has the opportunity for hydrogen bonding, but the hydrogen bond of an OH is stronger than that of an NH. Why? Just because the bond is more polar, right? The delta minus on an oxygen is a lot bigger, which gives the delta H a really, well, technically it's a lot bigger actually. And then here you have a smaller delta minus and smaller delta pluses. Why? Because nitrogen isn't nearly as an electronegative as oxygen is. That's it. That's all. There are many small molar mass, as I told you before I even started recording this video today. They have really unpleasant odors, okay? Really stinky smells. It smells like rotting fish. Like here are a couple examples. Putrescine, you've all heard the word putrid before. So putrescine and cadaverine, if you've ever smelled the odor of decomposing flesh or a cadaver maybe in the biology lab or in the anatomy lab, you might have smelled cadaverine. There's a rare metabolic disorder that causes the deficit in normal production of the flavin-containing monooxygenase 3 that gives people a syndrome called fish odor syndrome. It's where the body can't oxidize trimethylamine. So you have trimethylamine produced in your body, and normally it gets oxidized to what's called the N-oxide. And I know that we saw N-oxides earlier when we looked at N-methylmorpholine N-oxide or NMO. But basically what happens is since you can't metabolize the trimethylamine, it builds up in the in your sweat and in your urine and in your breath, and then it just ends up, persisting, and then the odor comes out, and that's fish odor syndrome. So if you want to Google that one, it's kind of interesting, very interesting, fish odor syndrome. Right. Anyhow, I didn't even know about fish odor syndrome until I saw a little news story about it one time. And being a chemist, I thought it sounded pretty interesting, so I decided to look into that a little bit. Well, if you took general chemistry 2, and you all did, and you all passed it, you would have talked about the basicity of amines. And you would have said, well, amines are bases like ammonia. It's a base, for example. It's a proton acceptor. Well, amines are actually stronger bases than alcohols or ethers, aren't they, right? We don't think about alcohols or ethers as being bases, but we do think of amines as being organic bases. Amines can, in fact, be readily protonated by strong or weak acids. This is acetic acid right here, acetic acid. It's an organic acid. It's not a strong acid. It's got a pKa that's higher than 0, right? It's got a pKa of around 5. But if you look at the equilibrium between triethylamine and acetic acid, you end up with the triethylammonium ion. So this is called triethylammonium, right? And this would be acetate. So you'd actually get triethylammonium acetate, but you look at the pKa here, it's around 11. Well, if the equilibrium is going to lie to the side of the weaker acid, it's definitely going to lie to this side. So what does that mean? The take-home message is, even if you put an amine like triethylamine in a weak acid like acetic acid, it's almost going to be completely protonated, right? You've got a difference of what, 10 to the power of 6 here. So that means that 1 in a million of the molecules will not be protonated or something like that. So you end up with a lot of protonated molecules. Now you should be familiarizing yourself with the pKa values of these ammonium ions here. Why? Because the basicity of an amine can be quantified by looking at the pKa of the corresponding ammonium ion. What do I mean? I mean the higher the pKa, the weaker the acid, and therefore the stronger its conjugate base. If you look at all the pKa values of all these ammonium ions on here, I mean, they have a bunch of them on here, but you probably noticed that they all have the same pKa values. They're all between 10 and 11, aren't they? Right? So again, the weaker the acid, what does that mean? It means the stronger the base, right? The weaker the acid is, the less of a propensity this has to give up the proton, okay? And therefore, the stronger the base. Now, here are some other amines that are shown protonated over here, like aniline or N-methylaniline or NN-dimethylanilin over here. And you notice that their pKa's are all around 5, okay, of all these protonated anilines. Now, why would these be stronger acids? Right, because they're less content to have these protons on them. What does that tell you? Right, remember that the higher the pKa, the weaker the acid, therefore the stronger the base. What does that tell you? It tells you that aniline is not as strong a base, for example, as cyclohexylamine. So that would mean, again, and I'll write it down here for you, that cyclohexylamine, okay, is stronger base than aniline. Right now, I bet you could all answer the reason why. It's because the lone pair that's on the cyclohexylamine is localized, whereas the lone pair on aniline is not localized, isn't it? We know that it can participate in resonance in the ring. Furthermore, if you look at pyrrole and pyridine, check out these pKa values. Right? If you look at pyrrole and pyridine, the pKa values are pretty drastic. You can see that this is all borderline a strong acid. If you protonate pyrrole, why is this such a strong acid? Right? Remember that the weaker the acid, the stronger the base. Okay? So this is a really strong acid, and so therefore this is a really weak base. Now, why would pyrrole be such a weaker base than pyridine? The reason why is because if pyrrole picks up a proton, the aromaticity is destroyed. Right? You go from something that's aromatic, okay, to something that is not aromatic or non-aromatic. Okay? Whereas here, both of these, even when you protonate pyridine, it's still aromatic. Okay? So that means that pyridine is going to be a much stronger base. Remember, the higher the pKa, the weaker the acid, and therefore the stronger the conjugate base. What about solubility of amines? It says here that in general, amines with more than 5 carbons are only going to be slightly soluble in water. When we have less than 5 carbons, they're going to be significantly soluble in water. Solubility is enhanced by the presence of an aqueous acid. Why? Because you end up with an ammonium ion and a cation, something that's water soluble, right? Let's say you take an amine, okay, a primary amine, and you put it in an acid like HCl. Well, we just saw that amines are bases, so this is going to pick up the proton from the HCl, and you're going to end up with what? You're going to end up with an alkyl ammonium chloride, right? This is essentially a salt, right? Not table salt, but it is a salt. If we have a salt, what does that mean? It means it's going to be water soluble, right? The salts are H2O soluble. All right. So amines can be extracted from organic impurities using an acid and converting them into ammonium ions. In fact, this is something that you would do normally in the wet lab. If you take the chemistry 3102 lab, you learn how to separate an acid compound. You actually do the extraction of a carboxylic acid, an amine, and a neutral compound, just an alkyl compound. So, okay, a neutral, an acid, and a base. Anyhow, but that's neither here nor there for today. Many pharmaceuticals contain one or more amine groups and are marketed as salts. Here are some examples here. You can see that Viagra is actually marketed as a salt, and I think there's a little blurb about Viagra in this chapter where he talks about how Viagra was originally developed to treat angina, and then the people or the patients who were in the clinical trials determined that there was, other side effects, and so they decided to follow up on those. You can also see compounds like Gleevec is also administered as a salt. So we have lots of nitrogens in pharmaceutical compounds. Again, the pK of most alkylamine conjugate acids is between 10 and 11, although we looked at the pK of arylamines and it was significantly lower, right? We had stronger acids, therefore arylamines are less basic. Why? Because that lone pair is delocalized, and I told you that you should be able to draw that. Now, if we have a substituent on our aromatic ring, that can affect the basicity of the aniline derivative as well, right? If you have an electron donating group like a methoxy, which can donate electron density, what's that going to do? It's going to make the amine or the lone pair more available. It's going to make this more basic, and therefore you're going to end up with a weaker acid. Whereas if you have something like a nitrile, this is an electron withdrawing group, and that means that this is going to be less basic, and when it's protonated, you're going to end up with a stronger acid. So the whole take-home message is that the stronger the electron withdrawing group on your aromatic ring, the less basic it's going to be. Again, we talked about the lone pair on the nitrogen of an amide, and we said that that nitrogen is actually sp2 hybridized because that lone pair is participating in resonance with the carbonyl. If you look at the electrostatic potential map of an amide, you see that most of the electron density is up on the oxygen. What does that tell you? It is not available whatsoever. And so an amide is not considered to be basic or nucleophilic. Why? Again, because most of the electron density, this lone pair has most of its electron density up on the oxygen like that. Now, we've talked a lot about acid-base chemistry, but we can actually prove using the Henderson-Hasselbalch equation why most amines are going to exist as salts at physiological pH. It says here at physiological pH 7.3, amines exist primarily as ammonium ions. So if you have an amine in your body, since you're at pH 7.3, it's mostly going to exist over here on this side in its protonated form. Why? Because the equilibrium is going to lie to the side of the weaker acid. All right. So for physiological pH, let's say the pH of your, body is 7.3, okay? And if this is 10 to 11, the pK of your ammonium salt, well, the equilibrium is going to lie to the side of the weaker acid, just like that. I'm not going to go over the proof given or using the Henderson-Hasselbalch equation. You can figure that out on your own. It's not very complicated. But again, most amines are going to exist as salts at physiological pH. Well, with that in mind, let's take a look at a couple of practice problems before we get into some interesting reactions. The first one says, rank this group of compounds in order of increasing boiling point. If I call this A, B, and C, in A, we have a tertiary amine. In B, we have a primary amine. And in C, we have a secondary amine. Could anybody tell me, would it be A, B, or C, which would have the highest boiling point? Which one would have the highest boiling point? Absolutely. It's going to be B. Highest boiling point because it has the opportunity for 2 hydrogen bonds. And A is going to have the lowest boiling point because it has the least opportunity for hydrogen bonds. Next, it says identify whether the compound is going to be expected to be water soluble. So remember that water soluble amines should have 5 carbons or less. We'll put here less than 5 carbons. Okay, and that should be per amino group. Okay, so if we look at this one, you get 6, 7, 8. So this one, you have 8 carbons per amino group. So this would be insoluble in water. So we'll put insoluble. Whereas the next one You have one amino group for 3 carbons, which is less than 5, and so that would be soluble. What about the last one? Does anybody have an inkling as to whether this should be soluble or not? Going off of this rule here? Yeah, I agree, Skylar. It's going to be soluble, isn't it? Because if you break it here, then you've got 3 carbons here for one amino group, and you have 3 carbons here for one amino group. So you still have less than 5 carbons per amino group, and so this will be soluble. We'll put here less than 5 carbons per NH2, just like that. Next, we're going to look at some compounds, some pairs of compounds, and we're going to determine which one is going to be the stronger base. Now remember, if the function of a base is to be an electron donor, right? Base is an electron donor, then the question becomes, well, I've got a lone pair here and I've got a lone pair here. Between these two compounds, which one of these is more readily going to give up its lone pair? Which one wants to do this? Right? If they both had a competition for H+, would it be this guy that would take it, or would it be this guy who takes it? Which lone pair is more available? If I call this compound A and I call this compound B, can anybody tell me in which one the lone pair is more available? It's actually A, because in A, the lone pair is localized. Whereas the problem with B, I know what you're thinking. You might think, well, couldn't I draw, some kind of Lewis structure like that? No, because then you're going to exceed the octet rule, right? You'd exceed the octet rule. But there is a resonance structure that you can draw like this. So when you draw the resonance structure of this compound, what you actually prove is that it is electron deficient. I'll prove it to you. Look, if I draw the other resonance contributor, it's going to look like this. Okay, we have a negative charge here and a positive charge here, like that. Okay, there we go. So a positive charge on the nitrogen and a negative charge here. And so since this pair is localized, but this one is delocalized. I can't spell low. That means that the answer is going to be this one here. Okay, let's try another one before we take a break. What about this lone pair and this lone pair? If I call the first compound C, for example, and I call this one D, could anybody tell me which one would be more available? And you might have to think back to your aromaticity days. You could actually look at this one and say, which one is less available? It's the ones in C that are going to be less available, right? Because the lone pair in C is required for aromaticity, whereas this lone pair is not participating in aromaticity, is it? Okay. You have 4n plus 2, or n equals 1. So if this doesn't participate in aromaticity, okay, then if that lone pair doesn't participate in aromaticity, then you have a Huckel number of electrons like that. Anyhow, so we'll just go with this one here. All right.